All right, welcome to the deep dive. We're digging into the sources you sent over today, and wow, they're all about the Copenhagen interpretation of quantum mechanics. Foundational stuff, but famously strange.
Definitely strange. Yeah, the materials trace it right back to, the 1920s. Niels Bohr, Werner Heisenberg.
In Copenhagen, hence the name.
Exactly. And they were really just trying to make sense of experimental results that, they broke all the old rules of classical physics. It was a huge shift.
Huge is right. The sources really drive home how counterintuitive it is, gets philosophical fast. So let's unpack it. How exactly does this Copenhagen view differ from, the physics we normally think about?
Well, the biggest leap, and your notes highlight this, is away from certainty. Classical physics is deterministic, right? Know the setup, predict the outcome perfectly.
Yeah, cause and effect.
But quantum mechanics, according to Bohr and Heisenberg, it's fundamentally about probabilities. A particle doesn't have a definite state, like position or speed, until you actually measure it.
Okay, hold on. Before you measure it, it's just fuzzy. Your articles talk about superposition. What's that actually mean?
Superposition, yeah. The readings describe it as the particle existing in a blend of all its possible states at the same time.
All of them.
Simultaneously.
Sort of, yeah. An electron isn't just here or there. It's potentially in many places or many states at once, each with a probability attached until
you look. This is the observation part the sources make such a big deal about.
That's the absolute core of Copenhagen. And honestly, the most argued about bit. The act of measurement observation. It causes what they call the wavefunction collapse. It forces the particle out of that fuzzy superposition of possibilities. It instantly picks one state, just one, and that's what you see. The probabilities vanish, and you get a single concrete result.
Wow. Okay, so measurement isn't just passively seeing what's there. It seems to, decide what's there. How does Heisenberg's uncertainty principle fit into this? The sources link them. Oh, they're tightly linked. Yeah, the uncertainty principle, as your notes show, says you just cannot know certain pairs of properties precisely at the same time.
Like position and momentum. The classic example.
Exactly that one. The more you nail down the position, the fuzzier the momentum gets, and vice versa. And crucially, Copenhagen says this isn't just because our measuring tools are bad, it's baked into reality.
A fundamental limit.
Yeah.
Okay. And Bohr's idea, complementarity, that things can be waves or particles, but not both at once.
Right. Depending on how you set up the experiment, how you choose to look, the double-slit experiment is the perfect illustration, which your sources covered well.
Ah, yes, the double slit. Explain that again quickly.
Sure. Send electrons one by one at two slits. If you don't check which slit they go through, they build up an interference pattern behind the slits, like waves would.
As if each electron went through both slits somehow.
Exactly, acting like a wave. But, and here's the kicker, if you put a detector at the slits to see which one each electron goes through.
Let me guess, the pattern changes.
Totally changes. The interference pattern disappears. They just act like normal little particles going through one slit or the other. No wave behavior. The mere act of finding out which path destroys the wave aspect. Observation changes the outcome.
Which brings us right back to those head-scratching philosophical questions your sources raised. If looking forces reality to pick a state, does observation create reality? Are particles only real when we watch them?
I mean, these are the questions that kept physicists up at night. Still do. It just feels wrong compared to our everyday world where, the moon is still there, even if nobody's looking at it.
Or we assume it is. And Einstein really hated this, didn't he? Your notes mentioned his famous objection.
Oh, absolutely. Einstein couldn't stand the randomness, the probabilities. He famously said, God does not play dice. He was convinced there had to be something deeper, some hidden variables we just hadn't found yet.
But despite Einstein's doubts and all the philosophical weirdness, your sources were pretty clear. Copenhagen works. Scientifically, it's been incredibly successful.
Undeniably. The math framework it provides predicts experimental results with amazing accuracy. It's, the standard tool used in quantum physics calculations every day. It underpins a lot of modern tech.
Still, it's crucial to remember, as the sources point out, it's just one interpretation, right? Not the final word.
Absolutely critical point. Yes, there are others, many worlds, pilot wave theory, and more. They all try to explain the same quantum math, but have very different ideas about what's really going on underneath. There's no consensus.
So Copenhagen is like a powerful instruction manual. It tells us how to predict what happens, but maybe not why it happens that way.
That's a pretty good way to put it. It's pragmatic. It gives us the probabilities. It describes the collapse upon measurement, and it works. even if the why is still, well, a bit mysterious.
Okay, so wrapping up, we're left with this picture from your sources. A quantum world that's fundamentally probabilistic, not certain, where the act of observation plays this bizarrely active role in settling what reality we actually see.
Precisely. It's a framework that matches experiments brilliantly, but it really forces us to question our basic assumptions about how reality works.
Which leads to a final thought for you, our listener, to chew on. If observing, has this much power down at the quantum level, what does that suggest, if anything, about the nature of reality on the scale we live in every day? Something to ponder.